So my presentation is basically, I think it was perfectly placed into this work program, since it's a bit of continuation of the previous two talks. I'll actually present some of the results of our project PERSIST. It does not have to do anything with rare diseases. It is basically focused on cancer survivors. But I think the principles of patient engagement and what actually are the fundamental problems in terms of AI in medicine, it covers very well for any direction. So Project PERSIST is actually, it ended in February. We just had our last, let's say, EC final review meeting in May. It was a let's say, mid-sized project. It covered a couple of countries from Europe, as you see on the map. And of course, we have 4 clinical sites where we carried out prospective studies with 160 patients. So what was Project PERSIST all about? It was to create an ecosystem where actually patients, AI, and clinicians are coexisting in the same space. And we are trying to integrate patient experiences, the real-world data that actually exists, into the clinical routine. So this is why somehow you see, yes, we have an app that communicates with the patient. We have, of course, chatbots that somehow deliver some storylines to help the patients. We have some software sensors that can extract features from how they communicate. And we have a system that helps also clinicians, let's say a decision support system that somehow helps clinicians to identify problems which they were not aware of. So to facilitate that endpoint, here we come to a bit of the AI parts that we use. So of course, we had to deliver a symmetric model of interaction, because if you want a person to respond using their natural modalities, you, of course, on the app has to provide some natural modalities as well. That's why we developed and delivered our own proprietary speech recognition system for 6 different languages. It was Russian, Slovenian, English, Spanish, Latvian, and French. So basically, 2 languages were completely non-mainstream with almost zero resources, Slovenian and Latvian. So it was a challenge, but AI can help you there. You cannot really, you can see some of the results. So basically, as you see here, one problem with AI. It works perfect in laboratory conditions, in research conditions. But when you put this acoustic model into the wild, when patients start to communicate, these word error rates don't mean anything. So that's why afterwards we had to add a spell checker, a language model to somehow compensate for the errors of noises that come into the data in real world. Then we come to the next, let's say, our proprietary software. This is text-to-speech synthesis system. Again, we had to develop it for all 6 languages in PERSIST. And again, in the test laboratories, it works perfectly. But when you do some Mushra tests with patients, you see there are errors. So you have to compensate. And we don't know exactly why the errors come, but I can tell you for sure, for instance, the main problematic language was actually Slovenian. Why? Because it's non-phonetic. So we don't do phonetic signs. So the pronunciation is sometimes completely off. 2 words are written in the same way, but they can be pronounced a bit differently. So the AI has really struggles sometimes to actually facilitate that. So using these technologies and, of course, chatbots, we delivered, in the end, this system where we have a patient recording a diary. Why a diary? Well, we tested with patient-reported outcomes. And in order to capture what actually patients are experiencing, you need multiple patient-reported outcomes. There's CRC30 for cancer survivors. Then you have psychological questionnaires such as PHQ-9, GAT-7. All those need to be facilitated. And in addition to some symptom-specific questionnaires. So doing this every day or twice a week, can be burdensome and also problematic. So zero long-term sustainability. It was shown that actually these patient-reported outcomes are great when you do it in a study, but in real world, they don't actually help. The other thing is patients will do it before they come to the appointment. So you have the memory loss. You have all these issues, psychological issues, that impact these patient-reported outcomes. And it's tiresome for them. That's the other thing. So motivation there, we also observe this in our studies. Even oncologist says, please do it, they will do it. And when they start failing, again, an oncologist has to say it, please do it. And then, again, the motivation increases. In any case, that's why we started to think about how to improve long-term sustainability. And of course, one aspect of it is do some pre-screening and just trigger specific patient-reported outcomes or Q&A questions when those occur. And how to screen? Well, the easiest way, ask patients as a semi-structured interview to record themselves and then extract certain symptoms from the text and then trigger the Q&A with patients so that also what you ask them actually reflects what they feel. Because most of the time, or many times, these patient-reported outcomes, the patients don't know how to answer. Not that they do not understand the answer, but the problem is they don't feel it. They don't think it's about them. So that's how we try to do it. And of course, now to provide the explainability of it, we actually also have to present something to the clinician. So basically, we provide the clinician with a text that was said by the patient, and there's an ontology-based system, basically a knowledge graph, that also tries to extract possible symptoms. And based on those symptoms, a chat is generated with simple yes and no questions to actually see where the symptoms might originate from. This is a proprietary software from another company, not particularly ours, so I don't have technical details on it. I know bits of it, but yes, it was not really our work. Then this is the implementation of it. Basically, as you see, we also do depression recognition. This was our take on how to start evaluating psychological distress of the patients, because a lot of patients, while they were actually using the app, reporting anxiety. You know, fear of reoccurrence. Actually, they were starting to relive the cancer period. So this is just a simple, I hope the video works, I do not know. Yeah, it's gone, it's, okay. This is just an end-to-end system. I don't think it will show you everything, but it's, you see, this is the Q&A part. So someone said, I have a fever, today I'm feeling a headache, this is basically symptoms. And what we do, we generate we extract what are the possible symptoms detected, and based on those, we feed them into an AI and then create Q&A to see a bit in more detail what happens or what are the reasons. And then we come, I will go to the next slide and I will come to back to this one. So then we come to, let's say, the final AI part that I want to represent. It's multimodal depression classification. So the most important thing here is, yes, well, AI is biased to data. This is one thing. And the other thing is all the algorithms are actually very low. The precision itself is very low. That's why that's basically state of the art. And that's why it's very important to understand why the classification was made. So what we did, we actually did a literature survey to see how people that are depressed express themselves. So what features can we find in speech? What features can we find in text? What features can we find in facial expressions that they expressed? And so basically, based on that, we defined a set of observable cues based on which we can now, let's say, explain, not in terms of post-hoc explainability of what AI does, but actually through observing the context of the individual. Of course, this is still a work in progress, and the problem with it is the feature extraction is, again, AI, so it really depends, the quality of the classification really depends on the quality of AI itself. And now, then we also had the decision support system inference. This is basically just the system. So the patient answers a diary. What happens is this diary triggers some symptoms that the clinician receives, and then clinician can trigger this overall interaction system and then analyze the results. we validated our solution in actually in a multi-center clinical trial. So we had this hypothesis that performing a comparison at the beginning and at the end of the intervention, participants will significantly increase their self-efficacy following up the personalized intervention. In addition to this application, of course, patients were given, survivors were given some advice. They had direct contact with the clinicians through the app. So there were a couple of elements that we validated. In total, we actually recruited 166 patients, and we had a dropout rate of 26 patients, which is not bad. But you see, the main reasons of the dropout were, of course, unforeseen circumstances. So someone moved, someone had a cancer reoccurrence, so that's why they had to drop out. But more importantly, anxiety and reliving the diagnosis was one of the most or the more relevant causes. So when delivering patient-reported outcomes or this kind of apps, actually, in a way, you are increasing the fear instead of relieving the fear. And of course, burden of questionnaires and diary recordings. So that's the other thing, and I do not know how to solve this one because we did it through a 2-year trial, actually, where patients were involved in co-creation as well, and we always had this dance and gone left and right with what is okay and what is not okay. But this one, I know the burden itself, I think it will be solvable when patients will see the benefit, the actual benefit. And we saw that when clinicians start to actually use the results in the follow-ups, the burden somehow decreased. So in terms of the answers, well, actually, activation level of patients was good in the beginning, so there was not much to improve. Most patients actually had 3 to 4 activation level for PAM, Patient Activation Questionnaire. However, results do suggest that any mHealth app, can support patients in improving their self-management skills. User acceptance was actually good, as you see, because it was a long trial, it was a 2-year trial, it dropped at the end, of course, because, again, patients were tired of using the app. So if possible, do not carry out trials that are too long. This is also our take on the study. So lessons learned, yeah, patients need feedback and they must not be let alone. So always you have to communicate with patients, you have to listen to them and actually then provide different versions of the application that actually showcase that their feedback is valuable. And the other thing is when we all like, at least in technical world, we like wearables. But we have to understand wearables are something that might be a problem because not all patients like to wear smart bands. Actually, they have issues while sleeping. This kind of elements are significant, and there have to be alternatives to patient-gathered health data than just automatic capture from wearables. And that's pretty much my presentation. These are some links that we have. The page will be online for a while, but as I said, the project has ended, and we are moving to the next one. Thank you.
Thank you, Isidore. Oh. Questions? First, Eric.
Yeah, thank you for your presentation. In the first part, you presented the different speech recognition models. And if I understood correctly, you have also analyzed what words they use when they described.
Yeah, so you use speech recognition to actually create sentences, and then you put that sentence through a knowledge-based graph to extract certain, let's say, keywords that represent symptoms.
Mm-hmm. Okay, so the question then that I have is, because you have different languages, did you map the language to the same knowledge graph?
Yes. No. I think, as far as I know, each language has its own knowledge graph, because the same as in neural models, the more focused the model is, the better is the accuracy. That's kind of the take on it.
Okay, thank you.
Thank you for the talk. It was interesting. I have 2 questions and 1 comment. One is, you mentioned you used multimodal data. And I was really interested in the sensors you used. Did you use geolocation, camera, wearables? What did you use?
So we used the smartphone camera. So the patients were asked, all patients got a smartphone. So we had one smartphone all had the same smartphone. So we provided them. This is so that we had the same resolution, the same camera, the same quality of microphones. And they got a really, really, let's say in parentheses, cheap smartband. Because what we know is if we provide them a 400 euro smartband, it's pointless. Because they will never be able to afford it. So we also wanted not to increase, let's say, health disparities by suggesting an equipment that would not be available to everybody. But the smartband was regular. It measured blood pressure. It measured heart rate. Well, the quality, it was okay, but it was not the best. And it measured also, of course, the steps.
My second question was, in terms of the data, how much data do you need? You had 116 patients included. How many time points did each patient have?
In terms of patient-reported outcomes, they did them, let's say they did them basically on a weekly basis. Okay. Specific questionnaires each week. But yeah, for 2 years. And for 1 year, each patient was asked to record a 5-minute diary twice a week, not more.
Did you simulate to see at how much power you have that way? Did you have enough power to detect different effects? I was wondering whether there's enough data for such a complex model.
I did not work on the decision support system, but the decision support system was based actually on retrospective data. Okay. So we also had the 4 hospitals contributed with about, I think it was about 30 or 40 gigabytes of electronic health records without images. So It was a lot of, it was over, I think, 3 million, let's say, patients that were in the model itself.
And did you have a psychologist working with you?
Yes, I have actually, part of my team are 2 psychologists plus a psychiatrist.
I found it interesting because what you've presented is quite controversial. You said you had sort of features that would help you identify emotions. Now, that's a very controversial topic in psychology because there's quite a bit of research showing that we experience the same emotions. We can have the same physical reactions to very different emotions. Yeah. And that's very controversial to say that. You can compare that across individuals.
No, we did not really measure. Of course, in the features, we do have emotions because that's what AI can give you, but we actually observe facial expressions themselves. Looking down, these kind of things.
Okay, so that
in the depression classification algorithm, because I know, smile is not really, happiness. It doesn't equal. Exactly. Yeah, I know that one. I know. No, so I misexpressed myself. It was not emotions that we are interested in, actually, but expressions that are occurring. But the problem with this is that we don't have data. So we have issues with data. So DIAG-VOS is actually an experimental data set. Again, it was a cohort. It was not really semi-structured interviews, but chatbots, so the sentences were not that long. Whereas Symptomedia data set, that one is trained professionals simulating various psychological ICD-10 diseases, basically for the teaching. So that's the problem. So we are actually now in a phase where we are preparing to create our own data set, where we'll actually, with our department in the hospital department of pediopsychiatry, we'll actually record patients during the sessions, and then we'll be able to actually get real data and how it occurs.
Okay, thank you. Any other questions? Okay, thank you. Thank you, Isidore.